Alright guys, here is the final lesson for chapter 8. We are looking at the sum of an infinite geometric series. So a couple things on this one. It's a super simple formula we'll get to in just a second. Couple things that have to be true about this. First of all, it's got to be geometric. So if you see a number pattern like this, where you can tell that there's the same number that's being multiplied every time to get the next term, we know it's geometric. And then the little extra thing about that is there's a certain requirement that has to be true about that value as well. So I have my son Tyler here to help me out with this video a little bit. So here we go. So Tyler, what number is being multiplied every time to get the next term in the sequence? What number? What number is being multiplied?
2.
What did they multiply times 2 to get 6?
3.
And what did they multiply times 6 to get 18?
3.
So it's the same number. So that number that's being multiplied is called what?
A common ratio.
The common ratio. So that would be our R value. Okay, so there is a common ratio, which means it's geometric. So the thing about this one is it's infinite because it's just a sequence that goes on forever. In other words, we're not having a specific number of terms. It's just finding the sum of an ongoing sequence. So because of that, there's certain requirements for when this exists. First things first, the common ratio that you see right here has to fit this description. Ty, what does that mean? What has to be true about the common ratio? It has to be a number between...
The 1 thing?
Between this? What's this?
The
-1?
-1 and +1?
You got it. So common ratio has to be between -1 and +1. If it's not, then you have to say that it's not possible. That's what this is describing. So I tried to put that into a friendlier terms so it looks a little easier to identify. So you only need the first term and the common ratio. Okay, there's no specific number of terms for this because it's infinite. So this is the sum of, that's my little infinity sign. Sorry if it's kind of ugly, but that's my infinity right there. So first term over 1 minus the common ratio. So it's super simple. I'm not going to go into a bunch of depth right now onto why this has to be true. For now, just keep in mind that's what has to be true. So let me flip over to our couple examples here. We're just going to look at a few. So I'm going to keep this short and sweet. So right here you can see this is that little sigma. That's our Greek letter for sigma. It's always asking you to find a sum. So this is based on this. We can see it's an infinite sum. So we talked about this in the last video, but this fits our geometric model that you see right here, right? This represents our first term. This represents our common ratio. And so we can just take that information and put it into the new formula that looks like this. So Ty, what's going in for the first term of the sequence?
6.
You got it. So 6 goes in for the first term. What's our common ratio?
3.
3 over
5.
Okay, so here's the question you got to ask yourself is, remember what we said on the last page, the common ratio has to be a number between -1 and +1. So Ty, is this a number? Is 3/5 between -1 and +1?
Yes.
It sure is. So that makes this an okay thing to do. If it was not, then we just have to say it's not possible, or you could say there's no sum. So anyway, this can go in your calculator. So if you just did 6 divided by 1 minus 3/5, definitely use parentheses. You should probably be using parentheses here as well when you type this in. So I would also do this just to be safe, especially if you're dealing with negatives and things like that. That's really important that you use parentheses correctly. So we'll just type this one in. So if you want to give this one a try for practice, go for it, buddy.
What?
You want to type it in?
Sure.
So hit 6 and then divided by, and then open up a parenthesis.
This thing?
Yep. And then type in 1 minus.
1? This?
Yep.
Minus.
And then open up another parenthesis. Put 3 divided by 5. and then close your parentheses twice because we opened it
Wait,
twice.
so press
So
twice?
this one. Yep.
Again?
Yep. There you go. So that's all we had to do to put it in. So our infinite sum on this is 15.
Fitting.
Pretty easy, right? Okay, so here's just a quick example. You'll notice on this one, this has a common ratio that's bigger than 1. So this is 2.5. If you see that as a decimal, that's easier. So obviously 2.5 is not a number between -1 and 1. So this is a case where you would have to say there is no sum. It's not possible. So real quick on these, just to give you a couple more examples. Again, plugging into our formula, you can see our first term right here is 5. The common ratio, they're multiplying by 1/3 every time to get the next term. So there's my common ratio. So rest is calculator, just like the last problem was, and this would be our answer. You don't have to write it as a fraction. You could write it as 7.5. That would be fine. But that's it. So remember on these, if you have a hard time figuring out what the common ratio is, you can always take any term and divide it by the previous term. So if I did 5/3 divided by 5, that's another way that you could figure out your common ratio is 1/3. One more for practice. So right here, you got your first term is 1/2. My common ratio is -1/2. And so if you simplify this correctly, you should get 1/3 as your infinite sum. Okay, and so that's the main thing. Let me show you really quick one word problem, because I know you guys love word problems. Everybody loves word problems.
We don't.
Whenever you are changing with a percent, that is automatically going to be the common ratio. It's going to be a geometric pattern. So this one right here is talking about a swing, right? So if you can picture a swing or like a pendulum kind of a thing that travels like back and forth and back and forth. Well, over time, if you were to just push a swing and then let it go, right? The first swing would be the biggest, but each time it travels back and forth, it's going to get a little lower and a little lower and a little lower and a little lower. And so it's going to keep getting smaller and smaller and smaller. So what this is saying is the first push, the first swing was 30. That's the first term in the sequence. But after that, as the swing slows down, it's only going to reach a height of 75% of the previous distance, right? And so it's reducing 75% of the previous distance on each swing. So that's our common ratio. So we're putting that in as 0.75, and the rest is basic calculator. So you would simplify this just like the way we did up above. And that's it. That's the end of chapter 8. Thanks for helping, Ty.
Mm-hmm.